The urban heat island effect occurs when modern, dense construction materials absorb and trap solar radiation. Across city centers, concrete and flat commercial rooftops act as aggressive heat sinks, forcing localized temperatures to spike far above their surrounding rural environments. These temperature spikes create immediate dual consequences. They place a critical strain on regional energy grids, from sudden surges in air conditioning demand, and they cause a measurable surge in municipal hospital admissions. This flowchart maps the core scientific hypothesis for mitigating this crisis. The strategy requires deploying two specific independent variables: applying spray-on reflective coatings to commercial and residential buildings, and integrating adaptive, smart HVAC systems into the local grid. Each intervention directly impacts a distinct dependent variable. The reflective coatings reduce ambient temperatures, lowering heat-related illnesses and hospital admissions. Simultaneously, the smart HVAC systems reduce total electricity consumption, lowering economic energy costs. The physical tools for climate mitigation already exist. The actual barrier is building a deployment architecture capable of adapting these tools to vastly different geographic, economic, and demographic realities across the country. The solution to this logistical bottleneck is hijacking the software architecture of an existing geographic asset tracking application. The physical foundation of this tracking app is built on a rigid transcontinental corridor, locked precisely between the 37° and 38° north latitudes. This exact coordinate plane provides the perfect testbed. By cutting straight across the mainland, it captures an extreme diversity of environmental data points, tracking everything from dense urban centers to high-altitude deserts. We establish what we call the UHI Enterprise Overlay. This functions by taking specific, localized software logic and layering it directly on top of static geographic markers. Mapping our two independent variables against this established directory changes the utility of the software. It now manages and automates climate interventions through the existing tracking interface. By marrying physical geography to node-based software logic, localized climate crises can be managed and scaled on a continental level. We start by defining the eastern origin point of our physical testing corridor to establish the baseline environmental metrics for the system. The domestic base coordinate is the Indiana Anchor Terminal. The terrain here is low-lying, wooded river basin country along the Ohio River, featuring dense vegetation. We can immediately contrast this baseline by jumping across the tracking corridor to the extreme western boundary of the domestic map. This is the Grand Staircase Escalante Terminal in Utah. The terrain is a stark shift into zero-canopy environments, highly exposed ancient geology, and brutal solar radiation. Because the underlying software architecture is uniform, it treats both the humid river basin and the arid desert canyon as identical data nodes. This ensures the mitigation variables can be dynamically localized without rewriting the code. Moving inward, we focus on the mid-continent hubs located squarely between the 94° and 97° west longitudes. The dominant physical footprint of these nodes consists of sprawling tech grids, heavy freight transport hubs, and immense industrial zoning. The Wichita sector, in particular, houses massive aviation manufacturing infrastructure, characterized by massive operational footprints. Directly east, the Joplin threshold features a high density of historic mining infrastructure and intense commercial development. The primary UHI challenge here is structural. These commercial nodes contain millions of square feet of flat warehouse roofing. Throughout the summer, these massive flat surface areas act as aggressive heat sinks, rapidly elevating the ambient temperature across the entire region. The localized software logic targets this specific infrastructure. The app actively pulls real-world energy consumption data directly from local utility company APIs. When a specific warehouse's heat absorption spikes its energy footprint past a designated baseline, the algorithm triggers. The app instantly flags the facility for physical intervention. In these industrial hubs, the climate dashboard operates as an automated economic trigger. It schedules reflective coating deployments based on real-time data, driving down commercial overhead while cooling the localized environment. Westward, at the 100 to 101° west coordinates, the tracking corridor enters the semi-arid prairie lands of the Dodge City node. The high plains present a strict environmental dichotomy: brutal, sustained summer solar exposure, operating alongside a heavy deployment of clean energy wind farms. This is a stark, high-altitude flatland reality. Massive wind turbines dominate the strict north-south road grid, capturing the immense atmospheric energy of the open plains. The required independent variable shifts for the specific geography. Here, the system deploys adaptive smart HVAC systems, programmed for continuous, real-time adjustments. The application ingests real-time weather feeds to constantly anticipate temperature spikes across the plains before they register indoors. The critical synchronization logic occurs next. The app forces the heaviest, most energy-intensive cooling cycles to run exactly during peak wind energy generation hours. By dynamically aligning cooling demands with renewable grid surges, the system significantly reduces the net electricity burden on the local grid during peak summer heat. The framework shifts when the corridor hits high-density transitional urban nodes. In these areas, the physical topography and dense construction create severe localized heat trapping. High-density populations surrounded by heat-absorbing asphalt and brick face a compounding physical danger during peak summer months, as the ambient temperature remains elevated even through the night. The dependent variable being strictly monitored in this node shifts from economics to biology. We track direct heat-related illnesses and hospital admissions. The software integration pivots accordingly. The application establishes secure interfaces directly with municipal health and hospital databases to track real-world biological outcomes. When a localized heat index crosses a deadly baseline and admissions begin to climb, the app actively flags specific high-risk residential grid squares. This precise geospatial flagging provides city governments with empirical, undeniable data justification for public-private partnerships to scale reflective coatings exactly where they are needed most. In dense urban centers, the software acts as a predictive public health triage system. It targets physical interventions with enough precision to save lives. Zooming out from the hyperlocal case studies, we can view the entire system functioning sequentially across the 37° to 38° north transcontinental line. The geographic tracking app and the UHI mitigation overlay operate effectively as a single unit because they share the exact same underlying tech stack. The first pillar of this shared stack is scalable field logs. The core database structure, originally engineered to log terrain metadata and ARTIS assets, is simply repurposed to log the surface temperature differentials between coded and uncoded buildings. The app accurately sorts these thermal files by precise longitude markers, maintaining pristine data integrity across thousands of miles of varied terrain. A robust climate management system does not require building new software. It only requires mapping critical thermal data onto established, scalable logs. The second critical pillar of the shared tech stack is predictive analytics. This chart illustrates the intersection of geographic elevation variables and real-time HVAC adaptation metrics. By cross-referencing these data points, the algorithm projects a downward trajectory in energy costs, allowing for precise financial forecasting before physical implementation begins. This structure provides a viable commercial model. It allows municipalities and private developers to financially sponsor specific geographic nodes along the tracking corridor. The value exchange is clear. Sponsors fund the physical deployment of reflective spray services in their selected regions. In exchange, they receive verifiable, audited data tracking and highly valuable carbon offsets. This precise tracking of regional impact allows massive enterprises and city governments to align their operations with strict 2030 climate goals. By overlaying climate interventions onto a geospatial grid, we have developed a data-driven framework for managing urban heat at scale.